Well, we have to introduce to you the concept of a common ion effect on the molar solubility. We saw the common ion effect in the world of the buffer, and we're going to see it here again and see how adding a common ion affects the solubility. The solubility, we're going to learn in what way it affects it, and we're going to be able to calculate the solubility after a common ion has been added. So let's consider this equilibrium. If we were to take the silver chloride and add it to a solution and have equilibrium be established, and then go in and add some sodium chloride to that solution, we would be increasing the amount of Cl- that's in that solution. The Chatelier's principle tells us which way this equilibrium will shift. Select your answer. Well, if you said it would shift it to the left, then you are correct. Le Chatelier's principle says that if you add a substance on one side, it will shift away from that substance to try to reestablish equilibrium. Now, if it's shifting it to the left, what can we say about the solubility of silver chloride? Is it increasing the amount that will dissolve, or is it decreasing the amount that dissolved? And I have it written the other way, decreasing and increasing. Well, if you said you're decreasing the solubility, that is correct. If we're pushing this to the left, there's more solid, less ions in solution. That, by definition, is a decrease in the solubility. So the common ion effect of molar solubility is always the same. If you add a common ion to this solution, it will always decrease the solubility of the salt. Now, it's important for you to understand that it does not change the KSP. KSP is a constant. That's the solubility product, and it's a constant, so that's not changing. But the S, the molar solubility, is decreasing as you add the common ion. So let's see how you work through one of these problems. I have magnesium fluoride, and I want to know its molar solubility when I have added it to a solution that contains some sodium fluoride. So the first thing is, if this is the salt that I'm dissolving, which one of these two ions is the common ion? Well, it's the F-. Now, when you work these problems, students struggle with writing the reaction because they want to take these two substances, I've erased the work here that I've done, but they want to take this and react them together. That's not the reaction. The reaction is the same reaction we've been always writing. We're taking the insoluble salt and we are dissolving it into water, or we're dissolving it. Okay, so we have the ions, that's aqueous, and we have two F-, that's aqueous. That's the reaction. We're using the same reaction we've always written. I will have an ICE table, and this is where it's different. I am placing some of this insoluble salt into this beaker. All right, I'm placing some of the MgF2 into this beaker. But this beaker is no longer just water. This beaker contains some sodium ions already and some F- ions because it's sodium fluoride. So the F- is a common ion, and it is already present. So I'm going to put a 0 under magnesium because there's not already present some magnesium. But there's already present some F-. Now this sodium fluoride, when it dissolves, breaks apart 100% into Na+ and F-. So if the concentration of NaF is 0.10, that's the concentration of F-. Now, a common mistake that I see students making is to try to incorporate this 2 somehow. It does not come into play in the initial line. It has nothing to do with the initial line. That 2 has to do with the reaction taking place, and that's always in the change line. So you're just plugging it in because you know right now, before anything happens with the magnesium fluoride, that there's already some fluoride present, and the amount already present is 0.10. So now our change line takes place. There's nothing different here. Some of the magnesium fluoride dissolves, and that's the molar solubility. For every one of those that dissolves, you make one of these and 2 of the fluoride. So now there's still a large excess, so there's some still sitting on the bottom. I'll have S here, and I'll have 0.10 plus 2S here. As I write the expression, the KSP expression, I will write it first. I won't even think about what I see there. I look at the reaction itself and I write magnesium and fluoride squared. Now I'm ready to plug in what I know. I know KSP's value was 6.9 times 10 to the minus, what is up there, minus 9. The magnesium is represented with S, and the fluoride, we look right here, it's 0.10 plus 2S, and now I'm ready to square that value. The S is very small, and it's so small that even if we double it, it's going to be very small. And we're going to see that this is true, but let's assume that that term can go away. And that leaves me with 6.9 times 10 to the minus 9 is equal to 0.10 squared times S. So if we divide both sides by 0.10 squared, we are going to have S equal to 6.9 times 10 to the minus 7. Let's verify that this was a good assumption that we made right here. If I double that number and subtract it from 0.10, is it still 0.10? Certainly. So that was a good assumption that we made, and that is the molar solubility of magnesium fluoride in the solution already containing a common ion. Now it might be a good exercise for you to calculate the molar solubility of magnesium fluoride if this were a 0 in pure water and see if that's bigger. If it's bigger, then certainly this was where you should be. It should decrease the molar solubility of this ion. So this is the end of our learning objective 11. We have learned how to calculate the molar solubility in a solution that contains a common ion. I'm going to work several more of these example problems as separate recordings that you may want to watch and work your way through so that you get really familiar with how to write the reaction and how to solve for your molar solubility.